So the last time we had a chat, we spoke about the amines. The first section really was concerned with the physical properties of these amines, where we find these amines in biochemistries, and of course synthesis of these amines. A lot of these ideas we should realize by now were sort of reviewed. For example, you saw that the amines themselves are nucleophilic and basic, sort of like alcohols, but of course a bit more basic and show greater nucleophilicity than the alcohols because of the low electronegativity of the nitrogen. Today we'll be looking at the synthesis, some synthesis that involves amines. So we're looking at the reactions of these amines. A lot of this as well is a revision. So for example, if you look at the acylation, we covered some acylation when we did aromatics, we covered some acylation when we did carboxylic acid derivatives, and of course the diazotization of arenes and alkylamines. We covered some in aromatics and some other earlier work. Nitrogen heterocyclics. Heterocyclics we already covered as well in aromatics, but of course now we're going to have a deeper treatise. So the only thing that's really novel to us is this Hoffmann elimination and of course these rearrangements, and they're sort of simple mechanisms to understand. So we move on. You can see here, for example, to form the amide, we use an amine and with the acyl chloride. Yes, so we have a nucleophilic attack followed by elimination of the leaving group to form this amide. Of course, instead of say using a mole of pyridine as base to mop up the HCl, all we got to do is we just add another mole of this guy and that will mop up the ACL, so it keeps the reaction a little bit cleaner. But of course some people will use that pyridine if this is a bit expensive. It works, this acylation works, we utilize it when we're reducing the nucleophilicity of the nitrogen, and of course we can also use that as a protecting group, or protecting group means when we're reducing the nucleophilicity. Let's have a look. So for example, here you and I know that this nitrogen is quite basic, so it is really a powerful activator. Yeah, so powerful activator is donating electrons into the ring by resonance. However, this desired product where this monobromination will not occur in the state that we're in right now with the pure aniline. Why? Because there's just, the ring is just too activated. You end up with multiple bromination. So what we do is tone down that basicity, or tone down that electron donation by adding the acyl group. The only disadvantage, of course, with adding this acyl group is that hydrolysis to remove it afterwards is quite harsh. But you can see the mechanism here is, first of all, we acylate, and then once we acylate, then of course we've lowered the electron donating ability of this guy, lowered the activation of the nitrogen, yeah, and so now we can achieve monobromination and followed by our deprotection. Hydrolysis, of course, of these amides can be undergone by both basic and acidic conditions. Here you can see typical nitro. So nitration of this species, this aniline, you and I know, typically if we nitrate with something like this, multiple nitration, this thing will blow up in your face. But what we can do is we can acylate, followed by the nitration, yeah, and then of course the hydrolysis will realize our product. Another advantage of this acyl group, of course, is that we produce some sterics. So you can see now that we're sort of reducing the possibility of ortho substitution. We covered in the past where the naked aniline in a Friedel-Crafts will not work. Yeah, it acts as a deactivator. Why? Because we have the coordinate bond to the aluminum trichloride, and now we got a pseudo ammonium, which is a deactivating species, and so that will be meta-directing. So what we can do is, again, we can acylate, and once we acylate, then the nucleophilicity of that nitrogen has dissipated, and so it will not bind to the aluminum trichloride, and so now we can carry out our Friedel-Crafts, yeah, without much difficulty. And then of course we can go ahead and deprotect. This is an interesting reaction. These are the sulfonamides, and all we got to do is react the amine with sulfonide chloride. It's a very, and we make these sulfonamides, the benzyl sulfonamide chlorides will react to form these sulfonamides. So let's have a look at exactly what happens. If we have a primary amine, yeah, the primary amine will react to give you a water-soluble salt on quenching with this base. The secondary amine will react to give you an insoluble solid. By the way, tertiary amines, which we don't have here, will be insoluble. These are some of the earliest known antibacterial agents that we generated in the past. So you've heard of the sulfonamide drugs, yeah, and they're still being used today. So a question I could easily ask is, what exactly is this Hinsberg? I think it was around back in the 1890s. What is the Hinsberg method used for? And of course, we could easily state that it can be used not only as a test, but for the separation of amines. The next species I want to look at is the Hoffmann elimination. All we do is we react the amine in the presence of a base. In this case, we got silver 1 oxide and an excess of methyl iodide. The reason for the methyl iodide, of course, is going to be predominantly a bimolecular attack on the methyl, with the iodine being the leaving group. And so you end up having trialkyl ammonium salt. The trialkyl ammonium salt will then, yeah, represent a rather good leaving group. So what we can, so you can think of sequential alkylation and so on, and 3 moles of them. We end up with this fella, and of course you can see that we can easily have an E2 across here. Well, this elimination, I should get rid of that E2 right now. This elimination, so we can show it here. This elimination is quite straightforward, but here is where it becomes effective, because if you notice, this amine has two different sets of protons that you can eliminate to form an alkene. So of course we can get the Zaitsev products and we can get the so-called Hoffmann product. The Hoffmann product is the one that dominates. So you can see here, elimination here. This is your leaving group. Yeah, gives you your Zaitsev. Elimination across here gives you your Hoffmann, yeah, i.e. the least substituted alkene. Look very carefully, yes, the least substituted alkene. Why, in this case here we have a monosubstituted alkene compared to a disubstituted alkene. That's of course sterics, because yeah, there's less access to the central part of the molecule than the peripheral part of the molecule. Something like this is kind of straightforward as well. Try to figure that one out for me. This is another question. This is another question that I think is quite nice. I want you to pause right here and see if you can resolve this. We will cover this in class. So pause at this moment and try to work on this, and then we'll review in the class. The next work, the next set of named reactions are the Hoffmann and Curtius rearrangements. Look at it carefully, yeah, because what they are is we have these amides. We can generate these amides from any carboxylic acid derivative, and we can convert them into primary amines. So here's our amide. This, of course, you can see the precursor of some sort of, yeah, carboxylic acid derivative, and here's our primary amine. The key step in the Hoffmann and Curtius rearrangement, I don't know why they call it a rearrangement, but it's a displacement of carbon dioxide. So carbon dioxide, so we have our group moving over into position here, and we're getting rid of this carbon. So it's a decarboxylation. So let's just go through the mechanism. You don't have to remember this for the exam, but you have to appreciate it. You can see here in the Hoffmann, right, we have sodium hydroxide with bromine, yeah, followed by hydrolysis, and that realized our primary amine. All we're doing is we remove with the proton, yeah, we remove a proton with the hydroxide to form this resonance stabilized amidic anion, which then attacks our bromine. Remind yourself of what exactly happens with an enolate. In the case of an enolate, this would be a carbon. And so now we have the bromine, yeah, on this nitrogen. And of course, you can see that further deprotonation realizes a species where we can have the rearrangement. So if I make this more cleaner, you can see that really what this is yeah. And there, this group, this R group, will migrate to that nitrogen with bromine being our leaving group. And that will give us our isocyanate. Terribly important, this isocyanate, because the isocyanate, we can do a wealth of things with it. And one thing that we can do with isocyanates is we can hydrolyze them. And when we hydrolyze them, yeah, then of course they give off carbon dioxide. And there we can generate our amine. It's no big deal, because remember now, if you look at it carefully, yeah, why, you can see that this is a sort of imine type system, isn't it? And so really you're trying to release this carbon. Now this carbon is going to become some sort of carbonyl, yes, right here, yeah, all right. And that's, so the whole net event is release of carbon dioxide, and then of course your amine. Yeah? So we've seen all of this before. When you look at the Curtius rearrangement, the Curtius rearrangement is quite simply, we can use, say for example, we use an acyl chloride with the azide to form the acyl azide. Once we form that acyl azide, then you can easily see the alkyl migration to the nitrogen with release of the carbon dioxide and dinitrogen. Yeah? I mean, once you see azide, you know there's going to be some sort of release of the very, very powerful, no, I shouldn't say powerful, stable dinitrogen. Again, you can see, yeah, once the dinitrogen released, then we get the isocyanate, and then of course we end up with the amine and the carbon dioxide. The mechanism for the isocyanate, yeah, being hydrolyzed to amines and carbon dioxide is quite simple, because this is something that you've come across before. There's an attack with a proton transfer, and then of course there's the elimination. So let's have a look at this law. This is Curtius, and this one of course is the Hoffmann, and all we're asking is for you to come up with the products. You can see, I'm just going to shorten this phenyl ring, of course, to make it a bit simpler and to manage them. So, and we just go ahead and just draw what we see. And of course, this is our acyl chloride, and we can easily, yeah, use that nucleophile, the addition elimination, i.e. substitution, to give us our azide. Yeah. You can see where we'll have the alkyl shift. I'm missing a carbon, sorry about that. Let's get rid of that, and let's do this properly. Happens to the best of us. So here's our azide. You can see where the alkyl shift will occur. Yeah, the alkyl shift can occur from here, yeah, to here, to form and then of course on hydrolysis you will end up with your product, which will be a puppy. At this present moment in your career, the stereochemistry is not that important. In the Hoffmann, of course, you can see that we'll end up with, in this case, we have your product, then your starting material. Your starting material will be chlorinated. And then from there, you can see that we would end up with our isocyanate, which you can see will give us our product. Ran out of space here, but I think maybe we can get it in. So yeah, I think we can just about get it in. So we get that amine connected to a tertiary carbon. I wonder what would happen if we used an alcohol to work up instead of water. Anyway, let's ask ourselves some questions. So for example, I have this one. It says here, which one is the main product of the following reaction of an amide? You can see immediately that this is the Hoffmann. Yeah, those are the Hoffmann reagents. So we'll convert and we'll discuss it in class. Yeah, and I'll pause it right here so that we can move on to the next one. Here we're asking the same question, and of course, yeah, this is the acyl azide. So we've done most of the work for you. You can recognize the Curtius, yeah, the acyl azide, yeah, and so you'd expect the Curtius rearrangement. So again, pause here, you work on that, and then we will discuss it in class. So from here on in, it's sort of like downhill, because you realize that this is the nitrous. We've worked on these before. We've not really looked at the alkyls too hard, but of course we looked at the diazonium, the Aryl diazonium in the past when we did aromatics. But you can see that with the primary amine, we can still use the nitrous, and we end up with this diazonium argon. Yeah, with secondary amines, of course, then we end up with a nitrous amine, and different implications. Yeah. Yeah, so the mechanisms are sort of quite simple. You have this this nitrous, which literally gets reacted with the amine, and with the primary amine, it's very unstable, and so we can see that it breaks down, and you end up with the diazonium cation. You can see same sort of thing happens if we have an Aryl species. Yeah, we end up with this interesting carb cation. So for the Alkyl species, then of course you'll end up with that carb cation. Yeah, sort of like it's a unimolecular mechanism, really, when you think about it. Yeah, releasing the very stable dinitrogen. So that's the driving force in that entropic events. You can see here the same sort of thing happens with your aromatics. Yes, and you end up with this Aryl carb cation. You want to keep it at low temperature. You don't want the dinitrogen to blow up in the face. Yes. All right. So we've seen this diagram before, just about any nucleophile that you can think of. Yeah, and then of course you can generate that guy. A lot of these guys, like the Sanmaya, for example. So you're using like here you're using sort of like some copper-1 cyanide or something. Yeah, and here you can use, for example, you can use the sulfurous. Yeah, you could use a copper-1 chloride, a copper-1 bromide, maybe a bit of water here. Yeah, copper-1 iodide, some borfluorine, fluoroborate. So for example, here you can see that we have the nitrous, and with this for us, then we can generate the naked benzene. The diazonium salts, yeah, can react without loss of nitrogen, so they can act as electrophiles, and you can see the nucleophilic attack of this phenyl ring onto the diazonium, and we end up with the species which is azobenzene. Yeah, and you can see that there is conjugation between this dinitrogen, N double bond N, and the two rings. They're quite nice in photochemistry because, as you can see, because of that extended pi conjugation, then of course we had the pi star, i.e. the homo-luma transition, that band gap is indivisible. So we move on, and now we're going to talk about nitrogen heterocyclics. And this heterocyclics remind ourselves that we're going to look at the chemistry of Pyrrole. We've already seen the basicity of the heterocyclics with the Pyrrole type nitrogens and Pyridine type nitrogens, but right now we're going to look at the electrophilic substitution, yeah, of Pyrrole, and we're going to look at Pyridine in two situations. We're going to look at electrophilic substitution, and we're going to look at nucleophilic substitution, yeah, on the substituted halopyridines. So why we want to look at heterocyclics? They're everywhere, yeah. So for example, these are some newer drugs, newer in the sense that over the past 2 decades and all that sort of thing, that's making a difference. We look here at the Pyrrole, and you can see immediately it's our old strategy, where what we do is we attack different positions on the ring and look at the resonance structures that we generate. You can see that with the substitution of the 3 position, we only have 2 resonance structures, while substitution at the 2 position, we have 1, 2, 3 positions. And so therefore the 2-nitro Pyrrole is the one that dominates. Yeah. If we look at, say, for example, Pyridine, let's look at first of all the electrophilic substitution, but we have a diagram here that says that's showing you nucleophilic substitution. So what we should do is get rid of this diagram. So if we look at the electrophilic substitution, again, it's our old adage where we attack the ring and look at the resonance structures that are generated, and we find that the 3 position is the one observed. Why? Because if you look at the attack on the 2 position, then you can see that we can't generate resonance structures that are suitable or in comparison to the one at 3 position. Because you see, for example, here we do not have an octet, so this is not very pure. Yeah, we do not see there is no divalent positively charged nitrogen out there, and so this is not a valid structure. So the 3 position is the one that is, we find substituted. So if you think of nitrogen as 1, then this position is 2, and this is 3. For the nucleophilic substitution, then of course you can see that again, why we think of this as sort of a pseudo mesenhyma. And if you look at this, these resonance structures, you can see here, we can push all the way through to here, but then pushing through to here is not very healthy. Yet here, this is a totally healthy situation, right? And so therefore the position at 2 is the one that is observed. Here's a Pyrrole question, and we ask you which one will be dominant. You can see that we haven't used a catalyst in this case. Why? Well, the simple answer is that the nitrogen is a little bit more basic, and so the ring itself is a fairly electron-rich ring, and so we do not need a catalyst to perform the aromatic substitution. I'm going to pause there so you can come up with an answer for me during class. So the spectroscopy, the main thing I want to look at with the spectroscopy is, of course, the infrared. And the infrared is going to tell you quite a bit. You can see that they're going to be these amines, yeah, that have NH bonding, are going to be in an area competitive with the OH, but of course they're less intense than OH. The primary amine, of course, will give you 2 NH stretches because of the C3V. The secondary amine will give you 1 NH, and of course tertiaries do not give you any NH unless you treat it with a bit of acid, and then of course you convert it into the ammonium salt with 1 hydrogen, and then you will see that NH. So for example, here we're looking at the primary amine, and you can see, yeah, this sort of sawtooth signal, and that, yeah, prescribes a NH2. You can see here we protonated the tertiary amine, and now we can see this NH from the tertiary species. In the NMR spectrum, proton NMR, yeah, similar to the alcohols, the NH can turn up just about anywhere between 0.5 and 5.0 ppm, and of course because the exchange is so fast, then we get broadening of the peak, and so there's no splitting. Yeah, if we use a deuterated solvent, of course, on the species, then of course the NH peak will disappear because of the exchange. And if you see the exchange between an NH and the deuterium, then now you have the ND, and the ND then is invisible to this NMR. As far as mass spec is concerned, then of course you can have alpha cleavage, and alpha cleavage realizes this resonance stabilized species, which you can, yeah, relate to, say for example, some sort of imine type numbers. Yeah, I think that's it. One thing you got to remember about the mass spec, terribly important, I should point this out, is if you have an odd number of nitrogen atoms, you usually have an odd molecular mass. So if you see an odd molecular mass in this course anyway, then usually, yeah, we're only going to give you something with 1 nitrogen in it, so usually there is an amine involved, or at least 1 nitrogen involved in the compound. I think that's the end of this. So the next time we have a chat, we'll be probing some mild introductory biochemistry, and so hopefully, look at that, the N of amines, and we will talk to you then.